humid temperatures in the truck, and you get it to site and you take it up and you turn it on. Now those pressure transducers might have drifted a little bit. They're reading a positive or negative number with no flow coming through them. We can quickly zero those pressure transducers. Basically what we do is we take the calibration curve and we move it slightly back to zero. So every time we start up, we know we're working with an absolute zero number with no pressure for accuracy on the instrument. And you can see there's a note here. This only works when the timer is at zero. So if you're operating the instrument and the timer is running, so you're recording how much sample time you're using, you can't accidentally zero your transducers, which would be catastrophic to the test. It would make all the information irrelevant. So it's kind of like a safety feature, that there's certain things you can and cannot do in the instrument, provided that other things are not working. You know, when the timer's running, the instrument thinks that you're in the middle of a test, so you can't change certain things because it's not allowed by the method, or it would completely destroy all the data that you're collecting. So we've got a unique and standalone leak test screen. So your pre-leak test and your post-leak test are recorded as separate values within the software. So you as a tester can prove either to the management of your company or to the customer that yes, we performed a leak test before we started sampling, and we performed a leak test after we finished sampling. We passed the leak test, and here are the values that we got. So again, you can provide reassurance to your customer that we are doing things correctly, and here is proof of that, right? With the manual system, sure, I did a leak test. See, I wrote it down. And they're taking your word for it. Okay, maybe they trust you, maybe they don't. Here in this, we can prove it's time and stamped in the software, and it's exported on that file. So again, you can prove to your client, we're doing everything the best possible way that we can. And here's proof of that. You can set your traverse points once you know how many and the duration of those. So maybe we have 12 traverse points for 3 minutes each. You can put that information in the software. And what it will do is it will not only collect the average information for that particular traverse point, so it'll record all of the averages for those 3 minutes and give you a value for that particular traverse point, but it will also alert you as the operator that you're about to change traverse points. So you can set it to say 15 seconds before I need to move the probe, start flashing the screen at me. So you're sitting there, you're operating, there's a lot of things going on, all of a sudden the screen starts flashing. You know you need to tell whoever's operating the probe, okay, we're about to change points, okay? And then it's going to flash, and then it'll stop flashing when you need to actually move the probe. So again, it's just adding functionality to help make sure we get the most accurate sample from the stack as we possibly can using this technology. And then we can also set a periodic save. So we can say, regardless of the conditions, regardless of where I am in my test, every minute collect all of the data that's coming. Just the raw data. Take a snapshot every minute, every 30 seconds, every 5 minutes, whatever you wish as the operator. So you can take 3 sets of data. You can take the traverse averages. You can take periodic raw data snapshots at whatever intervals you determine you want it to see. And then finally, we can take instantaneous ones by hitting a button. Something happens during the process, and you see a big plume of black smoke come out the chimney. You can just hit on the front of the console the Save Data button, and it will instantly save all that information. Then you can write down, save point number 2, black smoke came out. So when you're reviewing your data, maybe you have a big change in some particular values. Maybe it's flow rate, maybe it's temperatures, maybe it's something that was unique or outside of the typical scope of the work that now you again, as the operator, can report this to your customer and say, we had some strange event happen. Here I can prove to you that it happened. Here's the time and the date and the values that the instrument captured for us. So I'm going to do my best to explain this. It's quite a simple theory, but it's the best way to do this. So our pressure transducers take a reading 4 times every second, okay? So it's reading the flow 4 times a second. And as you can imagine, flow is never constant. It's always changing. So if we were to display the live values 4 times a second on the screen, you would have a number that would just continually change. There's no possible way that you could read it and make your adjustment at any given time. You just would not be able to see that value clearly. So there's a facility in the software that allows you to average those values depending on how much you want to see. So if I was to put an averaging size of 4 in there, it means it's going to give me 1 second averages because I'm taking a reading every 4 seconds. If I put averaging size of 20, obviously now I'm taking my 5-second averages, okay? So it's only going to display on me all of those averages over 5 seconds. So now I get a nice, stable delta P number that I can read and make my adjustments on, okay? So instead of having the liquid manometer kind of bouncing up and you look at it and you say, I think it's about the middle there, right? Now the software can do this for you. It averages it out and you've got a nice steady number, okay? Now the problem is if you make a move from, say, traverse point 3 to 4, okay? So you're jumping across the middle of the stack. It's the biggest move with the probe that you're going to make. And all of a sudden our flow rate increases or decreases significantly. We don't want to wait. Say we have an average set for 5 seconds. It may take a minute or 2 minutes for that average to slowly change to what those averages actually are at my new traverse point. By the time that happens, then I make my adjustment, I've been out of isokinetic sampling for well over a minute, okay? I might be sampling high or low, depending on the situation. So what you can do is you can say here that if any value within my average changes more than 5% or 10%, throw away all the old information and start me a new average. Okay? So if I've got a 5-second average and I'm taking 20 readings and one of those readings all of a sudden jumps from, it doubles, okay? Then the computer will automatically throw that average out and start a new one. So I get instantly updated a new average, maybe with a higher or lower flow rate, that I can now make the calculation with my K factor to get my delta H, to adjust my sampling rate, to get back to isokinetics. I hope that makes sense. I know English as second language is tough, and now I'm trying to explain this as well. I even explained to native English speakers, and they kind of scratch their head and they're not really sure. But if you've got any questions about that functionality, see me today, and I'll do my best to try and explain it a little clearer. So I guess we need to wrap up for a break here soon. Quickly for the software. The console can be used with or without the software on the stack. So it's up to you. A lot of facilities, at least in the US, do not allow computers or laptops or Wi-Fi enabled devices into the facility. It's a homeland security issue. So this is optional as an operator. But again, as an operator, you can see all the values on the screen, your temperatures, your flow rates, things like this. You can set up your job information, put all of the relevant site information in here that will print out on the report. So you can give that to your report writer or whoever in the office that will be looking at the final data as a reference. And then utility screen, this is a place where you can put in the values for recording your traverse points or your periodic saves or different things. And then calibration of the unit too. Doing a simple thermocouple check. It's very simple. It's not super clear there, but you can see, for example, this says our auxiliary TC, AUX. We can plug in a thermocouple simulator, or we can put it in an ice bath with a thermometer. And if we have a discrepancy in the reading, it's as simple as hitting a plus or minus button to get those two values to match. Then we can save it, and we've set an offset on the TC, and now that thermocouple is accurate and ready to be used again. So managing the equipment is actually quite simple as well with the software. So we can wrap up, maybe have a little break, have some tea, coffee, something, and then we can talk about the next topic. Does anyone have any questions before we wrap up this first session? No? And if you do and you don't want to speak out loud, come find me in the back. I'll be happy to discuss anything. So, all right, that's 1 hour of maybe 4 or 5 hours of you having to listen to me. So I appreciate your patience, and we're going to take a break? Yep. We'll have some coffee, and we'll resume in 15 minutes. Perfect.
มีคำถาม
as I said before, obviously, the public perception of PM 2.5 with the ambient monitoring stations in Bangkok is a hot topic, which is good, right? Bringing awareness. So how do we monitor PM size with our isokinetic kit, okay? And the way we do that is using our PM cyclone, okay? Something that we're going to add to the front of our Method 5 system, okay? So both systems are basically exactly the same. Same meter box, same impinges, same filter housing if you wish. But we're going to use this here on the front of our probe to measure or separate the size of the dust. All right. I'll pass this around so you guys can take a look at it while I'm talking. See what it looks like. You pass it around. It's pretty heavy. And then I'll show you how it works. So we'll talk about PM10 and 2.5 and quickly what it is. This particular cyclone and what it does during our cycling. Review the complete system again so you guys know exactly the equipment that you need for this testing. And then some limitations. It's not going to do everything depending on the site situation, moisture, things like this. So method 201A, okay? Develop this method and the procedures that a stack tester must follow to get filterable, and this is a key word here, filterable particulate matter emissions equal to or less than 10 micrometers and 2.5. So again, we're looking for dust that is solid, already solid in the gas. This will not capture condensable particulate, what we talked about earlier. Particulate that acts like a gas, but changes to a solid once it hits the ambient atmosphere. It does not account for this. So we're looking at method 5 kind of dust, but exactly what size it is, okay? So here's a representation of the size of the dust that we're looking for. So PM 2.5, you can only see with an electron microscope. It's very, very small, okay? And typically comes from combustion processes. So cars let out PM 2.5, forest fires, or maybe burning of crops here in Thailand as they change seasons, and industrial processes where a lot of the times we work. And PM10 comes from different kind of philosophies, whether it be mining or things like that, dust and pollen, naturally occurring dust particles in the air. And you can see this would be the average size of the human hair, and how many, or the size of PM10 and 2.5 when compared to the human hair. So it's very, very small. That's why they get into the human lungs and cause a lot of health problems. Now in the US, the EPA is already investigating and looking at PM1 sizing. And at Apex, we even have a PM1 cyclone that we can capture PM1 on a filter and see what's coming out of a particular source or things like that. So before 201A was developed, before 1990, other types of technology was used to do particle sizing. And some of this would be a thing such as a cascade impactor, where it had maybe 6 different stages in the cyclone to separate the PM sizing. And the way the cyclone, the cascade impactors work is each stage collects a different size of PM depending on things like the flow rate and the nozzle. So repeatability of that testing was very difficult. So they came up with the 201A method, looking for just those PM10 and 2.5 sizes, using a slight variation on the cascade impactor. And then, so for 201A, we are going to look at the 3 sizes. PM, larger than PM10, okay? PM10 in between 10 and 2.5, then everything smaller than 2.5. So there's 3 values here that we can report when we use method 201A. So some of the key things on this method when setting up for the method are selecting the nozzle size, and you can see on the instrument, on the cyclone, the nozzle sitting on the front. That will change, again, depending on things like your delta P minimum and maximum range, how much gas you want to suck through the cyclone. If you're interested in small particles, so isokinetic is required, but is not as important as method 5. So we are now plus or minus 20 on our isokinetic sampling as an approved for this method. So it's a wider range. So we have a little bit more leeway of getting an accurate result if we're outside of 100% isokinetic sampling, whereas method 5 is plus or minus 10. So it's half our variance. And then sampling point times are proportional to stack velocity, referred to as dwell times, how long you sample at each particular point, using constant rate sampling. So everything else is the same in the back end. So your impinges are the same. The materials you use in your impinges is the same. DI water, empty silica gel will be the same setup as method 5. We're just changing the filter from the hot box to a cyclone up the front of our probe. So you're still required to do a pre- and post-leak check, but you're only checking the system. You do not check the cyclone that's being passed around. So you actually remove that from the front of your probe. You do your pre-leak check, make sure your probe, your line, your impinges, and your console are leak-free. Then you attach the cyclone back on and start your sampling. So it's not quite the complete system for a leak check. And you can see here the sequence of the nozzle. It's the PM10 cyclone, the 2.5 cyclone, PM filter at the back, which is the disc at the back of that setup. Then your impinges to clean and dry your gas before it enters your dry gas meter. So your pitot coefficient number is going to be different than what you would use for your PM, for your method 5. So it's adjusted to make room for your sampling head. So there's 2 points here that I want to point out. One is that, and I'll see if I can show you here real quick. You can see here that just the same as method 5 testing, your pitot and your nozzle needs at the same point across the stack. So the same is required for your PM10. If you add a PM10 on the front of here, the nozzle will be out here. So you actually have to use an additional pitot tip to extend it further out so they're matching together, okay? So that's why you can see here on our probes, this is modular. You can remove this pitot, okay? PM cyclone on the front. And the PM cyclone attaches just the same way as the nozzle does here. It's the same size thread and same size connection. So for 201A, you don't need a whole new set of equipment. And the pitot, and you can go ahead and perform method 201A. So it's just an adjustment on the equipment that you already have. And hopefully everyone here has Apex equipment, so it'll be very easy for us to add those things on there for you. But most of the time, the EPA, they're not that. We can do PM1 only, or we can do PM10 and 2.5 together. The single PM, so 10, 2.5, or 1, it's a shorter cyclone. So it has one length of pitot. If you're doing the combination of 10 and 2.5, you need another extra length pitot to be able to, thank you, to do the sampling. So keep in mind, if you're ever interested in purchasing this and using this application for this method, make sure that you're getting the pitot as well with this instrument. They're sold separately, they come separately, and it also comes with a wind tunnel calibration, so the coefficient that we will give you with the paperwork on the pitot tip will be different, and you need to make sure that you use that in your calculations when you're sampling. So you're also taking into account that this PM head is much larger than a method 5 isokinetic nozzle. So you're actually blocking more flow in the stack. The smaller the stack, the more blockage that you get. So when we're calculating the coefficient for the pitot, we take into account that there's more blockage in the stack, and that again changes the coefficient number on the pitot as we calculate it. And then, just like we talked about with method 5, when you're changing ports and things like that, make sure you completely turn your pump off so you're not drawing ambient air into, or possibly PM 2.5 into the nozzle from the ambient air, and accounting for that in our stack emission. So when you've traversed all the points and you're at the end of the test, pull the probe assembly out and then stop the pump. Once it's clear, level, and stable, stop the pump and record the values. And the reason is you don't want the dust in here to shift or move within the cyclone, okay? So you're drawing the pump, you're drawing a vacuum to keep the dust inside the instrument where it should be when you take your final readings. If you have your probe and you turn off the pump and you push it down like this, the dust is likely to flow in the opposite direction. just like it would with a method 5. If you to push the probe down, maybe some of the dust would fall out of your nozzle or fall out of inside of your liner and go back into the stack. But you've already accounted for the gas that the PM or the particulate was in. So again, to get as accurate as possible, keep the probe nice and level, pull it out, take your readings, and then shut off that pump the last time. So the flow rate's a little bit different as we talked about. Again, we won't go into a lot of detail in the calculations, but it's important to maintain the flow rate through the nozzle to make sure that the cyclone here is cutting the size of the particulate in the correct manner as it flows around the cyclone. And that's, again, all based on the calculations that we'd have for determining our nozzle size and our flow rate and things like that. So this is our cyclone body here. So you can see this is our combination here of PM10, 2.5. So it's much longer. It's a pretty long assembly, much longer than this. So depending on what your requirements are and what you need to report, it may be a single like this, it may be the combination of both, depending on what your customer needs are or what the government's asking you to test for. Method 201A covers all of those variations, whether it be 10, 2.5, or 10 and 2.5 together, like that. So this is a really valuable slide here. It shows how the flow of the PM goes and where it actually sits within this instrument, okay? So everything here in the yellow captures our particle size bigger than PM10, okay? So that's inside of our cyclone around the outside here and inside our nozzle. So we're going to do that as a recovery separately and account for that as everything larger than PM10. Then, depending on the setup, but this is the combination setup, everything between 10 and 2.5 is going to rest within the body here, the gooseneck. This is kind of like a reverse nozzle on this back side. And in the PM 2.5 cyclone right here at the front. So I don't think we have one here, but basically this would sit right here in the picture. That instead of going directly to our filter here, we're actually going to have a second stage in between those two, in between these like this. So they actually, it comes out here and it goes down, curves down, and then this filter, the last filter will actually sit a little bit lower than the other one. So that's how it will look if you had the combination of both 10 and 2.5 together. And it would probably be about that long. So it's quite a big filter head on the front. And I think all of you saw, I mean, this is pretty heavy already. Imagine you add the PM 2.5 to this as well. It's quite a heavy combination. So keep in mind, the longer your probe, the more challenges you're going to have putting that thing all the way in and it's bending down, and it can be quite a challenge having that huge cyclone head right there at the front. So, and then finally, once you come down between the 10 and 2.5, the last stage here, in the filterable here, this last filter, is going to collect our sizes smaller than 2.5. So in theory, once you've finished sampling, you'll be able to report 3 numbers to your client or to the government. Everything bigger than 10, everything between 10 and 2.5, and everything smaller than 2.5, okay? And again, we can do any combination of those PM sizes with almost basically the same setup, just changing the pitot length and things like that. So let's take a quick look at, I think the next slide is, so this is a breakaway of the PM cyclone and all the individual parts and components that go into it. But basically, that guy there is our front plate on the front. We have an O-ring inside that creates a seal for us. Here we have our PM10 cyclone coming through, our nozzle size, and again, that button hook nozzle is specific to this design. It's the same as the design on the nozzles for optimum flow to allow the dust to flow correctly to the next stage of the cyclone to collect the particulate matter correctly. And then we have our PM2 section in the back with it's going to be a 47 millimeter filter just in the back here, like you probably use all the time. So again, this is the example of the one we have here, but that's just the PM10 or the 2.5 by itself as an individual assembly. And just like your isokinetic kit, I think it comes, typically we supply 7 method 5 nozzles. This will come with 12 different individual nozzles that you'll be able to select to after you've done your calculation and add to the front of your cyclone there. And again, they just have simply just a threaded screw that goes on. Just like you do with your method 5 nozzles, it's important to keep or protect the nozzle inlet from damage. You don't want to hit it or break it or change the circumference of your nozzle. That's important to accurate measurement. So make sure that the package that it comes in, it keeps nice and safe. No one's standing on it or stomping it or whatever happens. It's important to keep the nozzles in good condition for accurate testing. So this is an example here of the combination one that you can see. So you can see this is the regular method 5 probe, just like you all have, we have over here. But you can see here that we've got our PM 2.5 and smaller here in the back. All of this area here does our between 10 and 2.5, and then our larger than 10 right up the front. So you can probably see from this picture there's one difference in this assembly. So comparing this and this, they look a little different. This one here in the picture has this bracket around it, okay? So you can see it's on there tight. But if we were to open this, this is threaded, okay? It just screws in and it threads together. The problem is, with high temperature in stainless steel, the threads are going to, in English we say gall. They're going to stick together. And then it's almost impossible to get the sample out, okay? It's basically just going to be a paperweight. At the end of the day, it's going to be useless, okay? So if you have high temperature applications, we have a non-threaded version like this. So in the middle, can we open this by any chance? on the outside, okay? It just fits in there together, no threads. So then we use that cage around the outside to hold everything together, okay? So in high temperature applications, when the threads would stick together, now we have no threads. It's just a smooth fitting. So in a worst case scenario, when we've done testing, and we take it out of the stack and we take it back to the lab and we try and pull it apart, the worst thing we're going to have is that we cannot remove these bolts, okay? They are threaded on the outside, but it's a 50-cent bolt from the hardware store that we can buy at any time. So if we need to, we could just cut these off, pull it apart. Now we can access our sample, do our analysis, go to the hardware store, buy some new bolts, and away we go, okay? So not only do we have the non-threaded in a stainless steel version, but we can also do Inconel as well for really high temperature and maybe high acid, SO2 or something like that environments, okay? Because, you want to be able to use this as many times as you can over and over again. So keep that in mind when you're thinking about doing PM sizing 201A. Think about what your source is going to be like. Is it hot? Is it wet? Does it have high gas content? And which particular design will be the best for your application? And again, at the end of the day, the bolt together one, the no thread version, will work in every application. This one will only work in the lower stack temperature applications that we're getting it apart. Okay? So those are options that you need to keep in mind when we're doing this. So again, I already talked about this, but the pitot location is key. So again, the nozzle and the pitot need to be in direct line, just like they do with method 5 for the pitot and the nozzle location. So if you're doing 10 and 2.5, you're going to need a longer one. If you're only doing 2.5, you need the middle kind of size. And method 5, you just need your shorter pitot length to be able to make sure it works correctly. So this schematic here is directly out of the US EPA Federal Code of Regulations. This is published by the US government, and this is how they recommend the setup to be, okay? So this is our cyclone here on the front. We have our probe, just like we always do. Method 5 probe will work just fine. Screwing on our cyclone and adding our unique pitot length. And then you can see there's no other filter. It's only the filter in the front. There's no method 5 filter, nothing there in the hot box. So you go directly into your impingers. So for a method 201A sample, you would not have the method 5 hot box, which is this guy right here. So this one here does not exist. And everything are at the front, okay? You come directly down the probe, and then the next stop is going to be your impinger bucket. So we have a that mounts directly onto the impinger bucket. So it's a much smaller setup than method 5 as well. Dry it up and things like that. You come out, that's your umbilical line, your sample line, and then all of this is included here in your console. whether it be a 502 or the 572 or whatever console that you're using, exactly the same as your Method 5. So this is some of the challenges when you're doing Method 2 or 1A that may or may not be restrict you from doing this method. So the first one is if you actually have so much moisture in the stack, it's like raining inside. It's actually condensing and dripping down inside the gas or inside the stack. So it's going to basically clog up or wet the filters, make the PM behave differently, clog up the nozzle. It's just not going to be a good application for this, okay? So what you want to do then is you're probably going to look at doing it in conjunction with that method 202 I've already discussed, which is the condensable particulate method, which has a filter in the front and a filter in the back, okay? So this is a restriction. I don't know how often you guys would see stacks that are that wet, that it's just moisture continually raining inside, but at least in the US it's quite rare. Then obviously the stack diameter is a determining factor. Because we talked about before, the cyclone head is so much bigger than an isokinetic nozzle, it's blocking a lot of the gas from flowing up the stack. So if it blocks more than 6% of the area, you shouldn't be doing method 2 or 1A, okay? So really, if you're looking at doing a PM10 and 2.5 cyclone together, the extra long one, you need a stack that's bigger than 26 inches, so bigger than 2 feet, to be underneath that 6% limit of blockage within the stack, okay? And then if you're using just PM 2.5 head, the smaller one, the individual one, the stack needs to be greater than almost 19 inches to be able to have the minimum amount of blockage flow that you're allowed per the method. Now again, just as we discussed earlier, sometimes per the method we should have 2 ports, but we only get 1, okay? You still have to perform your testing. As long as either the regulatory agencies or your customer is okay with you blocking more than 6% and they need a number, maybe you still can on an individual basis. But if you're following the method exactly, these are the values that you need to think about in terms of the size of the stack and the size of the cyclone head. So maybe sometimes if you need both 10 and 2.5 and you've got a smaller stack, you need to do them separately, okay? Maybe you need to do 2.5 with a single cyclone, then go back and do PM10 with a different cyclone to be able to report those 2 numbers. Now, it seems like here in Thailand, at least 2.5 is the value that most people are concerned about at this particular time, which is correct. It's got the most harm and the most threat to human health anyway, 2.5. So session we could wrap up a little early, but does anyone have any questions about 2.1a, how a cyclone is, how you adapt it to a method 5 system? Any questions like that? Either you guys are embarrassed or I'm a really good teacher. I don't think I'm a good teacher. So again, if guys have got any questions during the break, let me know. We can disassemble, we can pull apart that cyclone if you want to see inside it and how it works and how we attach the filter to the backside there. So I guess we're going to break for lunch for a little while. Then after lunch, I'm going to talk about PS11 and doing a correlation study with your method 5. All right, so how a PM-SAMS works and how to put a value to the output signal that comes out of that instrument. Without a correlation study, without determining what that value means, the information is useless. And unfortunately, in some places like India, they've spent the last 3 years installing PM-SAMs. There's an estimated 25,000 of them in India. And I would say only about 5% of them have had a correlation study done. So they're getting these values coming out of the instrument, and they're really meaningless to anyone who's looking at them. So to do it correctly and to do it accurately, we'll talk about how those two values are paired together to get a nice solid number. And then we'll finish the day with mercury sampling. I don't know if you guys are aware, but the UN has an initiative called the Minamata Convention. It's based off the name of a town in Japan that had a huge catastrophe with mercury, and it affected a lot of people. So there's now a UN initiative called the Minamata Convention. It has more than 75 signatory countries now, so it's international law, and it's about the transportation and the emission of mercury. And if any of you guys have done mercury sampling via method 29 or on the Ontario Hydro method, it's very complicated, very cumbersome. It takes 8 or 9 impinges with wet chemistry. It's an absolute nightmare. So we have some new technology called method 23 with sorbent trap sampling for mercury, which is now the reference method in the US. It is the #1 method for doing mercury. It's quite simple too, so I'll explain that after our afternoon break as well. But during the break, if you guys have got any questions about 201A, the cyclone, anything on the internal working of the 202, I saw we've opened up the back of it. I can explain how the pressure transducers work, the size of the pump, any questions that you have, maintenance, anything like that, just come and ask me a question, let me know, and we could take advantage of the instrument being here today. So I guess we can take a break? Yeah.
เดี๋ยวก่อนที่เราจะเป็นที่ระลึกหน่อยนะครับตรงอุปกรณ์หน้าอุปกรณ์นะครับผมขอเรียนเชิญนะครับผม
Not sleepy after lunch? Fall over? Okay. So, any questions from this morning on 502 or 201A, the method? Does anyone have any questions? No questions. All right. Excellent, I hope. Okay. So, excuse me. So, we're going to spend an hour or so talking about PM-SAMs and how to correlate or install them correctly. What is required between the PM-SAMs and isokinetic sampling to do what's called a correlation, matching the two values together to get a good number. And I already mentioned to you that India is a good example. They have maybe 25,000 PM SENS. A very, very small number has been tested for accuracy. Now, in India, all PMSEMs are reporting a value. I have no idea how they get that value, but the installation is probably in most cases not done correctly. So I think everybody here has a good understanding of Method 5, right? It's very simple, very basic. So we can expand on our knowledge of Method 5 and talk about how we use Method 5 to test our PMSEMs and get an accuracy of that instrument. I think my clicker is... maybe dead. Batteries, maybe, or is it turned off? Okay. Perfect. No? So we'll talk about PM-SEMS technology, and there's 5 or 6 different types of technology that you might see for looking at PM-SEMS. We'll review PS11, which stands for Performance Standard 11, and we'll look at correlating the PS11 instrument with Method 5, and then some of the challenges that you'll see. So just to clarify, you have US EPA methods, then you have US EPA performance standards. And a performance standard are the rules for an instrument that need to be measured against a US EPA method. So the